E. coli is a bacteria that causes many distinct problems in humans, and because of its structure, is resistant to antibodies. Part of its resistance is the unique structure of its cell wall. Bacterial cell walls are often made of peptidoglycan, which is composed of long chains of alternating NAG and NAM molecules, which are sugar molecules that, when bound, have significant tensile strength. There are two types of cell walls that are important to discuss: gram positive and gram negative. Gram positive bacteria have a thick cell wall, whereas gram negative bacteria have a thinner cell wall and an overall more complex structure. There is a gel like matrix that sits just between the cell wall and the plasma membrane. Now, there is also a second lipid bilayer known as the outer membrane that sits just outside of the cell wall. This helps to envelop the cell wall in two membranes and provide extra protection to bacteria itself. The gram-positive bacterial walls are linked through pentaglycine cross bridges, but the gram-negative bacterial walls are directly linked. Because of these key differences, the cell wall associated with gram-negative bacteria are often more resistant to antibodies. Penicillin, one of the first antibiotics ever used, is able to act on the E. coli seen in the video due to the way that it binds with the plasma membrane. Because the outer membrane is a lipid layer that blocks passage of water-soluble molecules like penicillin, it acts as the first line of defense against the antibiotic. The membrane, however, has channels on it that penicillin can still pass through, thus giving it access to the interior. Once past that first layer, the antibiotic has no trouble passing through the gram-negative bacterial cell wall and binding to specific proteins on the cell membrane. This is in part due to its very small structure. This activates the penicillin, which disrupts the NAM and NAG sugars that create the cell wall, causing the whole thing to collapse. Now, it specifically inhibits the activity of enzymes that are needed for the cross-linking of the peptidoglycans during the final step in cell wall biosynthesis. It does this by binding to the aptly named penicillin binding proteins. This causes the cell wall to weaken since there are now fewer crosslinks, and water begins to uncontrollably flow into the cell. The cell then bursts and dies. Now, this doesn't mean that it acts equally well on all types of bacteria. See, penicillin inhibits peptidoglycan production. It actually works best on gram-positive bacteria that lacks the outer membrane, since it can just automatically plow through it and doesn't have to deal with the lipid bilayer. The composition of the cell wall is different depending on the type of bacteria involved, so it would really just depend on the type of bacteria that it is binding to. In addition, some bacteria have grown a resistance to penicillin, thus making it much more difficult to have an effect.